Okay, so, right. The paper I'll be discussing today is logic and lattices for distributed computing. We're lucky enough that it's one written by our professor, Dr. Peter Alvaro. Let's see, so let's get started. Now, Peter and I, 45 minutes is quite long for a presentation. So months ago, he and I had grand plans to conduct a live interview for the class, since he's the idea, Kyle, you had to do something similar, but I think that we could present better than him on his own paper. It's a little like Doug Terry's sort of, who are you lecturing toward? So, but then the Qualcomm thing happened, or whatever it is, the London trip. So that fell through, but not without me having spent time preparing for that. Including, I sent him some questions for him to answer in lieu of a live interview. But and everybody gets a free pass, but he didn't get around to doing that. So this is the best I could come up with in a short amount of time. I think it's pretty good. So that's I got gotcha. So okay, yes. Why did I also preface with that? Well, also in talking with Peter, we all have different strengths. It's been fun getting to know everybody, their speaking styles and different papers, sort of luck of the draw. But I've had a concern about my particular strengths versus a technical analysis of a paper. But he's been very encouraging, and that's been made me feel very welcome. So I feel pretty good about it. But he still said try to do at least like 15 minutes of good technical routing, even though clearly if there was an actual problem of understanding, and anyone really was concerned that this paper could be important for your future, email Peter, and that should fix that. But anyway, so these are like his questions that he's been telling everybody to look at. Yeah, it was a boon, and I made a little form of his questions, and so we have to do like a one-pager for every paper that we read from the syllabus. So I've been doing this quite a bunch. So since I was sort of in a pinch to prepare this, I just decided, well, why don't we just do another one of these as a part of the pedagogical requirements. So table of contents, for every one of the little things that there was an option at the beginning of the class that maybe we were all going to share our paper summaries with one another on Piazza. That fell through. I think there was something about Drupal originally that fell through. So several things have fallen through. But for all the ones I've written, I've done sort of a little quote. So a little quote. What problem does a paper solve is important? How does it solve a problem? Alternative approaches, other work, and research questions for yourself. So that's what we'll go over. So opening quote type thing. Well, I heard that Carlos was going to be our substitute today. And if you didn't know, it's right on his website. Also, you spoke to our 200 class, and that was one of the more memorable parts. But so we like this French sort of existentialist cat who is annoyed at the world. So the tagline is, "I am filled with ennui," which means like an annoyance, and party mix. So that's a good one. But also, this is just from his Twitter. My favorite is this is of recently. I'm afraid that after careful consideration, I've concluded that I cannot be your Valentine. So that's sort of characteristic of this sort of cat Twitter. So I like ennui. So that's it. Sort of a mental weight to lift before we get into logic and lattices. Okay. So what problem does paper solve is important? Well, I think so. Particularly, I've come up with something that I'm calling Alvaro's Law. I'm concurrently in a programming language class, and so I've used this particularly. I think I don't know if it's true or not. Again, I'd love to jab with him about it, but blah 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 blah. I assume that that's relevant. Maybe you read it. All programmers must now be distributed programmers, like period. because of the ubiquity of distributed programming. I mean, that's kind of like a big deal, if true. Certainly, the results of 10 weeks studying this stuff, it seems to be true. And yet it's not really being like embraced so much in 203 or in a lot of my other experiences. So I would like to see more of Alvaro's law in the world, as it might be, as it's a crisis and an opportunity. So does the paper solve an important problem? Yes. Okay, so how does it solve the problem? It's basically, this guy, which I wonder if that's in London. Bloom L, I think the L is just for lattices. I think a lot of us do know, but just for the so there's been like Bud, and then Bloom, and then Bloom L, and then there's Boom in there somewhere, and Daedalus. This team, what are they? The Berkeley Orders of Magnitude team, I guess, his little research group, have been doing distributed languages stuff for quite some time. It looked like, as far as bloomlang.org goes, that this is sort of as far as they got. I'm not 100% on that, but at the high level, it seems like the Bloom L is just basically the Calm theorem does seem interesting. I'll go into that a little bit more, but it just the Calm theorem plus lattices. What are lattices? Lattices are just kind of like fancy algebraic structures that have properties which are valuable in certain systems and that happen to be valuable for this system. So at a high level, that's what Bloom L is, I think. Okay, so and this will sort of follow the structure that the paper, if I'm dissecting, sort of doing a postmortem on his paper, I'm sort of just following along in their sections. So what is it? Why did we need a new language? There are lots of inefficiencies, sort of that what they call latency and availability costs. And so I guess the Bloom team, we're trying to address those by developing a new grammar. And so they mentioned two ways to handle these expenses. Convergent modules is the one for this slide. We just went over CRDTs. But CRDTs, according to the paper, there's some lattice fragility. Basically, if your grammar doesn't embrace lattices correctly, you can sort of go out of bounds fairly easily, and it puts cognitive stress on the programmer. And one of the, not only is Bloom an attempt to deal with these expenses, but also to sort of remove cognitive load from the programmer. I think somewhere on the internet, I've got it cited somewhere, a programming languages guru or something was saying, programming languages should be like platonic ideals. They should first be readable by programmers, and then only secondarily processed by machines. And that's easily disagreeable with, but certainly that seems to be the philosophy that the Bloom team goes with. And then also, there aren't guarantees with CRDTs, something like that. And if you put those two together, it creates a scope dilemma. So it's easy to sort of go out of scope. Just like we want the scope of this recording to be local and not global. So, but if we didn't handle that correctly, if I was unreliable or something, it could easily get somewhere where we didn't want it to go. That's a kind of the task. Okay, and so here the other sort of template or option for dealing with latency and availability costs that's discussed anyway is monotonic logic, which is I think one of the strong points from Berkeley, as that's heavy in their Calm theorem. So they use this term. I'm guessing they made it up, or at least this sort of confluency. But that's basically just eventual consistency. It's just sort of seems like the exact same thing, just with a different word. Sort of yoga confluence. Also, why did I put it? Because I'll get into that in a second. But lots of things are distributed. We live in an increasingly distributed world, and that's probably a fairly new thing. So what is their column theorem? This probably does deserve a little attention. So the big, I mean, I'm very interested in this concept, but if you like actually discover something new, and it's like a big deal, or it's relevant, like what do you deal with that? How does I mean, of course the process is you give it to a conference or something, blah blah blah. But anyway, the column theorem looked like a pretty big deal as far as I could get. But so basically it says as long as I'm going to go ahead and read it. They probably spent a lot of time wordsmithing this. So logically monotonic distributed code is eventually consistent without any need for coordination protocols, distributed locks, two-phase commits, paxos, etc. So that's like if you set up your sort of your system monotonically correctly, you don't need all these extra sort of jury riggings. Which would be like, that's, I mean, I don't know, it seems like it deserves some attention. And then further in the column theorem, eventual consistency can be guaranteed in any program by protecting non-monotonic statements, so points of order with coordination protocols. So that means, yeah, you can have the majority of your system be monotonic, and so it won't need locks and stuff like that. But if for whatever reason, because of the nature of modern computing, you do need some areas where there isn't monotonic logic, you just call that a point of order, and then you put in your locks there. So you have this, so that it brings some clarity to when you need locks and when you don't. So basically, according to the theorem, I guess maybe they need like lots of fancy proofing and whole completeness theorem or something before that's accepted or disproven by somebody else. But according to them, as long as it's monotonically correct or whatever, no need for locks. It'll be eventually consistent. It'll be confluent. And if you need to sort of hack in some areas that aren't monotonically correct, that's where you put in your locks. And so you isolate, you localize areas where you have to put in these sort of workarounds, essentially, that we use in very common, sort of band-aids, sort of duct tape to make the thing all stick together. Okay, so that one may be important. So again, it's just basically the column theorem plus lattices over their sort of, we heard some about the Boom language before. And so what are some of their claims about it being sort of state-of-the-art or worthy of a PhD? The language is liberal because you can have monotonicity over arbitrary lattices. So the lattices that, if we remember from CDRTs, lattices can be fragile. And yet their claim is that you can have sort of arbitrary lattices, and so the fragility of lattices is sort of taken care of for you by their grammar. And so it's sort of easier, you can sort of hack around hello world, I start with 10 or whatever. You can sort of, it's less pressure on the programmer to get that right. So, and then the scope problem is ostensibly fixed also. And again, you can use lattices without as much, Bertrand Russell set theory problem, halting, whatever it is, you don't have to worry about it as much. It's something that I'm a fan of. Okay, so this is from his personal website. But disorderlyprogramming.org or com or something, that's funny. I've asked him about that. And I've read part of his interviews and stuff. But basically that's kind of, what he's talking about is this old Netflix thing. But it's like, if you allow yourself to program in a disorderly manner, you may actually run into bugs ahead of time. You may find that rather than extreme attempts at how many years of computer science been going on? Long time. Lots of very smart people. Most of them, their predominant strategy has been extreme technical precision, and yet there's still I don't know, almost uncountable amounts of disorder in our field. And so his sort of funny theory is that, well, I mean, maybe we shouldn't be so precise all the time and sort of just, program it, work. Just like Fonzie. Fonzie, Happy Days was a classic television show in America, and a very cool guy named Fonzie. The jukebox would break, and the only way to fix it, no one could fix it, he would just go and just like hit it, and it would work. And occasionally hitting stuff works. I think that's kind of his disorderly programming philosophy. But anyway, so then there's a bunch of stuff in the paper after he goes through Common Theorem and all that, where he sort of explains how Bloom works. But the high levels, it's declarative. So like SQL, you can just sort of say stuff. It's over tuples, so that's going to be your basic units, which again, at a fairly intermediate to advanced level of programming, all that's fairly fine. There are like 3 phases of time steps, a little more complicated, but again, if they're just trying to make it easy for regular people to program, then it shouldn't be too much, and just a lot of their, worthy apparently of a PhD. I will talk more about it later, but I think there's also a meta disorderly programming, which is, if this is Peter's shtick, then he's not here. There's all these there's been a series of, you've been here like quite a bit actually, but we keep forgetting this little plug-in thing, and there's all kinds of strange little disorders. And yet I've had a very, I think, educationally fundamental, but fun and, sort of all the best things about college, especially graduate school, despite or maybe because of the disorderly programming that, we experience. So, okay, this is his friend. I also, in interview questions that I had prepared, I said, well, should I email your friends who helped you make this? I mean, I don't do that. But if you're just dying to learn about this, I've watched this. It's a good one. He explains all the technical stuff that I'm sort of glossing over to some degree. So there you go. I can post this in case you can find it there. Just search for it. Okay. So calm analysis. Everything you get for any given input, all program executions result in the same final state, regardless of network non-determinism. That's like eventual consistency or confluency, and calm is great. Essentially, is what they're saying, and that's for analysis. And then they have a bunch of stuff about language, and this is a very popular sort of computer sciencey internet cartoon. If you guys. Somebody isn't aware of that. But, there are lots of, one pattern that's been in our course so far is that there have been a lot of papers, the famous FLP, according to the GitHub, with just super intense technical sort of proofs and sort of explanations, which are great. But certainly not really my area of expertise, and I sort of have permission to sort of gloss over it. But it's all there if you want to look at it. And I'll sort of round back out about that closer to the end of the talk. Okay, this one seemed pretty important. Semi-naive evaluation. So the BloomL, the program will evaluate over the entire database because it's sort of a query length. So you've got a database, you sort of go over the whole thing. And the sort of the heuristic, the sort of clever trick, is that by being full naive, it would go over the whole database, and then it would go over all iterations of previous. There should be a lot of redundancy. And then their sort of clever trick is that, well, you don't actually have to go over all of the derivations. You can, through some algorithmic magic, only go over a portion of them and still get total knowledge. Any ones that you only skip ones that are pure redundancy rather than, well, maybe I really missed something. So that was a nice feature of the language. So there's a case study that is just sort of, you kind of just have to do that for proofs or papers and commentaries. Okay, yeah, here's an example where it worked. That's fantastic. So there's one, and he sort of explains that. And then they have another one like, oh, well, you know, a dynamo and like your shopping cart, which is sort of like one of the now canonical distributed system examples. And, you know, it works. They probably, I mean, occasionally papers will publish saying, well, we tried it and it didn't work, but that's probably the minority. So anyway, it did, in fact, work. Basically, so maintaining whatever properties that they want for Amazon, I suppose it's easy to gloss over because the main thing is you want the shopping cart to be, you know, functioning to a degree, and then you especially want checkout to function to a very high degree. And so this, I think Peter has another paper purely about shopping cart examples. So basically, by saying that it works, using BloomL in a shopping cart, I think they actually may have used Dynamo example, they maintained all of the desired properties for that particular business, such that you know, I was in Best Buy earlier, and the guy next to me was saying there's only one cashier. He said, hey, you know, I could just like yell, I could make a scene, and we could get more cashiers down here. I said, oh yeah, that probably works. He goes, no, that works every time. When you're dealing with something like Amazon, there are these actual variables of like people yelling at you or the apology. These properties become like the business, you know, basis. And I've been on Amazon many times, never had any trouble. So, and BloomL ostensibly could be a language behind the carts. So, what alternative approaches are there? Are they adequately discussed in the reading? Yeah, they have a related work section. A lot of it, if you read it, you know, you can all raise your right hand and swear that you've read it. But basically, I don't think it's a bias. I think when you actually, so far in my experience, when I've come up with new things, and I've written papers about it, you know, it's not even like trying to sort of use rhetoric, but all of the examples that were brought up were like, well, yeah, it's good at X, but bad at Y, and we're great at Y, and really Y is what you really want. So the related works all show like, yes, you know, and then my cousin Ginny is like really cool. He drives really fast, but he can't, you know, pass math. And, you know, cousin Bobby, you know, is a math genius, but, you know, no one will talk to him because he has no social skills. But me, you know, Peter Alvaro, the Bloom language, like I have a nice car, it's not that fast, and I can talk to people, and people like me. So really, you know, choose me, you know. So that's ostensibly what is almost in every related work type section. Very rarely does someone go, well, you know, I'm great, but really you should be using Chubby. You know, I don't know what Google's doing, but their implementation of Paxos is the best. So just try to get your hands on that. Yep. Okay. Okay. So how does this work relate to other research? We've got maybe 15 minutes, but probably not all that. Wow. Hopefully you're all familiar with that. Okay. Yeah. Basically, one thing, what have I gained in this course? These are in all of my paper reviews. This has been one of my favorite sections. I keep seeing sort of distributed principles that we've been learning. Because distributed systems is kind of new. We've been learning new things about it, relatively. But I keep finding that principles that I've learned in class I can apply in my real life. So, for example, the whole Alice, Bob, Carol thing, and just how easy it is for messages to become miscommunicated, where, you know, Alice sends one to Carol, but Carol already sent it to Bob, and so then Bob's replying to Alice as if he already knows what she said, but she doesn't know that he knows that she said it. That whole thing. So in daily life, I mean, just the amount of miscommunication that they're probably hugely unaware of. They become, you know, sort of that's the mad tea party, the whole Alice in Wonderland sort of philosophy, you know, may have some real bearing. The more that we are able to precisely pinpoint all the aspects of certainly computer communication, but then apply that to natural language communication. So that's been one of my very fun takeaways of thinking about life as a distributed system, and what does that mean given what I know about distributed systems in computing. And so then also, I think this is a really excellent example of that to try to think about. So when you look up at the stars or whatever, I'm pretty sure that this is like a physical fact. So like light speed exists and all that. There are stars that you'll be looking at which are actually burnt out, but because of the nature of time and space, the light is just getting to you at this very moment, even though it's traveling at 186,000 miles a second. So you're looking at something that took place, perhaps 20,000 years ago, and is now like extinct. But it's to you in real time, it looks as if that aspect of the universe is happening right now. So again, that may have physics may be telling us that indeed the reality in which we live is a distributed system, and so it is a very complex one, and one that we probably know very little about. And so this class has relevance to other work, and I think perhaps very profound ones. So here's more related works. There's like 7 billion people or something. It's a lot of us. And that's a sort of another distributed system. If there's some sense of unity in our species, or a whole bunch of us. But one thing that I'm working on in my own work is talking about a sort of planetary programming language. So eventually we're going to probably teach everybody programming, and eventually it's going to get into high school, and it just seems inevitable. Obama is given $4 billion to teach everybody in high school. So this is our customer, or whatever. This is our audience. There's the classic phrase "preaching to the choir." So the reason why you don't preach to the choir is because they've already read the Bible. Anyway, and this is from Ho Chi Minh City in Vietnam. But it's quite a difficult proposition to be thinking about how to deal with a planetary programming language. Do I think BlueMel, quantum analysis, is one that we should teach all people? No. Does it mean that I think it should be thrown away? Certainly not. You can take it as like an elective course or something. But thinking about these sorts of large-scale things, is something that I like to do and that I like sharing about, and I think could be done a little bit more sort of just in our general computing societies. So specific research questions for me or whatever. This is Peter's Twitter. Hi, Peter. He quoted me. That's me. From one of my little write-ups. I would say at some point, computer science is going to need to sit down and have a heart-to-heart with itself. My amazing students, and I got 2 retweets and 17 hearts. So I went and looked and was like, oh, that's fine. So, but what did that mean? Well, I can explain it more in a second. Just that this, I think you have some tone of it, but I've been really struck by this class. I'm getting old in my years now, and I've been around computing for some time. But so I'm not expecting every year that I take a class to be really moved. Like, wow, this is why haven't I heard about this before? Have they been hiding this from me? And then whoop, yeah, distributed programming. But like Alvaro's law from before, it seems like computer science may, it's sort of this giant machine that's rushing forward, but maybe it should I think further, he didn't quote the whole thing further. Said, it should maybe need to stop. Right? I don't know, IEEE or ACM could say, hey guys, maybe we should be more concerned about this distributed